Okay, let's continue mobile communication in chapter 3, where we will present the GSM radio interface and we will do some dimensioning exercise and we will see how the planning is done. And after that, we will explain the mobility management. So in the previous chapter, we already presented for GSM the architecture and the different components that are used within this architecture and what are the functionalities of the different component. So we investigated the user equipment or the mobile station, and then we presented the different component of radio subsystem, including the base station controller in the base station. And for the core network, we investigated the different component, the different equipment, including mobile switching center and visit location register, and also the home location register, the authentication center, and the equipment, the other let's say entities. Okay, so here we will start in this chapter by going into the details of the GSM radio interface in order to understand how this radio interface is defined in the standard. We will see the frame hierarchy, the logical channel, and the timing advance. Remember that in the previous chapter when we presented the range of the cell, we say that the macro cell could have a range up to 35 kilometer, and I asked you to remember this number to see why it's 35. Okay, so after that we will see some radio network planning process, and mainly we will focus on dimensioning. We will do some exercise, and we will see how to achieve the link budget, and finally we will investigate the different handover, the mobility management context to see the different handover, okay, in GSM. So let's start with the radio interface. In GSM, the radio interface is FTDMA, which is frequency time division multiple access, which means that we have the spectrum that is divided into different frequencies. The bandwidth of each frequency is 200, sorry, is 200 kilohertz. And then at each frequency, we have a TDMA where we have a frame structure or time slot. The frame is with 8 time slot, okay, from T0 until TS7. So that's why the resource that could be allocated to a user is a time slot, which is a certain time within the frame at a specified frequency. So that's why we call it temporal and frequential window, and it's used to transmit the information. Okay, that's what we allocate to a user. And what's the duration of a slot? The duration of a slot is 0.577 millisecond, which means that it's 577 microsecond. If we multiply this by 8, we have the duration of the frame, which is 4.615 millisecond. Okay, so what's a channel in GSM? So after knowing the GSM radio interface, how it is standardized or how it is designed, let's see together what's a channel. So typically, a time slot is the what we call the physical unit that we want to use for a channel. So if you want to have a channel in frequency, it's one carrier, which is one frequency. So if you want to use what's the physical channel, it's one slot per frame. So imagine that here we are at F6. So this is one frame, and after that, it will repeat. So this is the second frame. So here you will have TS0, TS1, TS2, TS3, and so on. If I want to say that I want to have one physical channel, which is TS0, this means that I'm using TS0 at this frequency. It's TS0 and so on, which is one physical channel. So it's one time slot. So it's one time slot per frame. So at certain frequency, okay, at a certain frequency, we have 8 physical channel. For a frequency, we have 8 physical channel because we have within a frame 8 time slots, and the channel is one time slot per frame. Okay, so if you want to know what's a logical channel, okay, the logical channel is, it's, let's say, a conception where we want to use the physical channel. If I want to use one logical channel is equal n physical channel, this means that I want to allocate a user one logical channel which is mapped to two physical channel, which is equal to two physical channel. In this case, this means that this user is allocated two time slot within a frame. Okay, this is what we call in this case one logical channel, which is using two physical channel. Okay, it's also possible that to have n equal 1 over 2, for example. In this case, okay, if I have, this is the frame, and here I have 8 time slot, and here I have the other 8 time slot, and so on, 8 time slot. If I say that I want to have one logical channel, which is half of physical channel, this means that more, let's say two users in this case will use, for example, each of them one half of the physical channel. But for each of them, we allocate one logical channel. This means that the user will use the time slot of the channel. The next one, the user will not use it and will use the next one. So in this case, within two frames, the user will use only one time slot. Okay, this means that it's approximately like he is using, or the user is using, a half of time slot over each frame. So it's one physical channel, okay, over two frame. This means that like one half of the physical channel over one frame. So that's why here there is another user that will take as TS0, for example. Okay. So this is what we call n equal 1 over 2. Let's say if you want to have, let's say, a logical channel that is equal to 1 over 10 of a physical channel, this means that the user will use the time slot, and after 10 frame, the same user will use it, and so on. This means that you can have 10 users that are using the same physical channel. Okay. I hope that it's clear for you the difference between logical channel and physical channel. So the physical channel is the time slots per frame. Okay, so in one frequency you have one physical, you have 8 time slot. This means that you have 8 physical channel. The logical channel is the channel that you allocate to user based on the physical channel or physical time slot. Okay. And as we said, what's the GSM channel is a repetitive channel is one slot over n slot. This is what we call, it's possible to have a repetitive channel, okay? It will be repeated every certain frame, okay? And we have also, regarding the channel, we have two type of physical channel. We have physical channel with fixed frequency and physical channel with hop frequency. In physical channel with fixed frequency, it's like what I presented before. It's TS0. Okay, we still at the same frequency. That's what we call with fixed frequency. If it's with the frequency hop, in this case, according to a predefined algorithm, how to shift from one frequency to another, it could be TS0, and after that you move TS0 here in F3, and after that in TS0 in F5, and so on. This is with hop frequency, okay? And we have two other type of logical channels. So I'm talking here of the physical channel, and let's see the two type of the logical channel. In logical channel, we have two type of channel. We have control channel that are used for signaling, and we have traffic channel that are used for data transfer, for the transfer of the data, okay, or of the user data, user communication, so user information. And typically in GSM, we have those two type of logical channel. Okay, so after presenting the radio interface, how it is designed and what are the different channel, okay, let's see now the different channel in uplink and in downlink. So we have in GSM what we call duplex, let's say distance between the uplink and the downlink frequency in both uh, uh, 900 megahertz frequency and 1800 megahertz frequency. And here in 900 megahertz, we have around the difference is 45 megahertz. We have here a kind of 124 24 channel, which is 124 times 200 kilohertz, and we obtain the overall bandwidth. We have a shift of 45 megahertz, and we have the downlink frequency channel. Okay, and typically, as we will see, the channel are duplex. This means that you have for a channel you have a bandwidth for the uplink and another one for the downlink. Okay, and the possible you have also in 108 sorry, in 1800 megahertz, the distance is 80 megahertz, and you have around 374 channel. Okay, and the possible transmission rate that are available are from 4 to 30 kilobits per second for voice, and it's possible to have around 12 kilobit per second of data. Remember that we are talking about GSM, and GSM, it was the second generation, and those bit rate was considered as acceptable for the services provided at at that time. Okay, so now okay, we apply other technologies. So typically, if you want to have what's a physical duplex channel, it's a channel that is corresponding to a frequency at the uplink and another frequency at the downlink. If we consider the case of GSM 800, so if I want to know what's the F downlink for a certain for example, frequency we have, as we said, 124 channel, physical channel. So I can consider that this is the low frequency. If you remember, this is 935 megahertz. So FD will be 934 plus 200 kilohertz. Okay. And I will find also plus 400 and so on. So I know the frequency of each channel. Okay. And as we said, a mobile will send and receive a different instance. So you have 3 time slot in time difference between the uplink and the downlink. Okay, this is a very important part. Okay, so if you have here, you want to define the uplink and the downlink, you have you just need to subtract the distance, which is 45 megahertz in GSM 900 and 80 megahertz in GSM 1800 megahertz. Okay, so this is typically the different channel uplink and downlink. Okay, as we said, we have for each physical channel we have let's say 2 sample channel, as we said, one at the uplink and one at the downlink, and this is what we call the duplex physical channel. Okay, and if you want to see at the radio interface what's the unit of transmission, so at each physical channel we will define the concept or what we call burst. What's a burst? It's really the unit of transmission of the radio interface in GSM on a time slot, and it's typically a certain number of bits. Okay, it's a quantum of transmission in GSM, and the duration of transmission is during one time slot. This means it's during 577 microsecond, and it's typically known as 156 bit plus 1 over 4 of the bit. And the bit rate, if we divide this number of bits over the time, we will receive 270 kilobit per second. And this number was typically the theoretical bit rate, the maximum theoretical bit rate that we can obtain using GSM time slot when we applied the GPRS technology. Okay, GPRS technology, it was the first technology used on GSM in order to send data and to offer internet service. Now we are not using GPRS, we are using Edge. Okay, I don't know if in Lebanon we still use GPRS, but I'm sure that we are using Edge. With Edge, we are able to use bit rate up to 3,184 kilobits per second. This is the double or more than this one. Okay. So this is the burst. So in this burst, which is 156 bit 0.25, in this case, we have 3 bits here as a let's say as a preamble, and we have 26 bits that are used for pilot. It's a sequence used. If you remember, when we talk about how to estimate the parameter of the channel, if you remember, when we say we want to estimate the channel, we have what we call pilot signals. Those are the sequence that are used to learn about the channel. And we have the information that are 68 bits here and 58 bits here and 58 bits here that are the data to be sent. Okay. So here, as we said, the learning sequence here is used in order to let the receiver know exactly the position of the signal within the window of reception. And as I said, it's also used to learn about the radio conditions of the channel. And for the burst, we have two types of the burst. We have the axis burst and we have the normal burst. In fact, all bursts that are used in GSM are normal, except the case where we have axis burst. And this axis burst is typically used in uplink direction during the initial phase. It's just when you want to access to the channel, so you need to use the axis burst on uplink toward the base station in order to solicit, in order to ask or to request a channel. Okay. So typically this is the axis burst, and as it's the axis burst, it will use the random access channel here, and all are for the synchronization, and here is the guarded period, and all other bursts are the normal burst as I presented before. We have the tail here, and we have the payload, useful information, and we have here the, as we said, the training or the learning session sequence or the training sequence. Okay. And you have always the guarded period in order to start the other burst, and the time of this burst is 577 microsecond. Okay. So at this level, we presented the important, let's say, terms and important features that are at the radio interface of GSM. Let's now continue to understand what's the time advance. Okay, we said that for us, we have the time slot. Okay, at certain frequency f, we have TS0, we have TS1, TS2, and so on until TS7. And if we have a base station, okay, and we have a user here, okay, we know that we have a kind, we know that we have a propagation delay, okay, because we are using on wireless, so there is some delay even at that level. And the duration here of the frame and of the time slot is in millisecond, and for that time slot is in microsecond. So that's why if I want to allocate this time slot, let's say TS1 for the mobile station, the synchronization is done at the base station, and the data or the information received at the should be received at the base station at TS1. Okay, this means that when we say that we should have a good synchronization and TS1, the physical channel TS1 is allocated to the mobile M, this means that the information sent by the mobile M should arrive at the base station within the time slot TS1. So in this case, if the mobile will start sending at just at the beginning of TS1 here, due to the propagation delay, it's not possible that those information will arrive at the exact time. So that's why we need a kind of time advance in order to anticipate. It's a kind of anticipation to let the mobile start the transmission before the exact time slot, to be sure that the information will arrive at the base station at the exact time. So that's why this will depend on the position of the mobile in comparison to the base station. That's why we have a kind of time advance code over 6 bits. So we have up to 2 to power 6 values in order to represent at which time the mobile will start in order to arrive at the right position. And typically, if we take, for example, a distance around 550 meters, it corresponds to 3.69 microsecond of go and back and round the trip. So that's why if we want to see here it, so you know that the duration of the frame is around let's say 577 microsecond times 8, which is less than 5 millisecond. And in this case, we should be sure that we cannot send the information from from a user before 5 millisecond. Okay, so that's why the maximum range of the base station is 35 kilometers. Okay, because if you have a cell range more than 35 kilometers, in this case the user should start send the information before more than 5 millisecond, and this will not be within the same frame and will not have a good synchronization. To be within the 5 millisecond and taking into account the propagation, the velocity of the signal velocity, in this case the maximum duration is 35 kilometers. Okay, so the time advance that we have here, we have different value. As we said, we have 2 to power 6, which is 64 values. So they start from 0 up to 63. And 0 means that the user is close to the base station. It's within a distance less than 550 meter. For example, the value 4 means that it's between 2 kilometer point 2 and 3 kilometer point 7, and so on. And the 563 means that the user is a maximum duration, the maximum distance of 35 kilometers. So in this case, the base station will inform the user using the time advance at which time this user will start the transmission in order to reach the base station with the right time slot. So this is the case without using this time advance. For example, if let's take mobile A and mobile B, in order to arrive to the base station, This is really the time slot of mobile. This is the time slot of mobile A, and here is the time slot of mobile B. And we can see here that the mobile B sent to the base station. Due to the propagation delay, it will arrive at this position. And here it's close to the base station, so it will arrive here and still be not finished the transmission. Here we have a collision. In order to avoid this collision, we will ask B to send before the time slot. This is the time advance. So B will start according to its position, will start the transmission in order to reach the base station at the time slot. In this case, it will end at the end of the time slot. And here A also will start sending before the beginning of its time slot according to its position sent by those values, and it will arrive at the right time slot. And here we avoid any collision, and the information of each mobile station will arrive at the base station at the correct time slot. Okay, I hope that it's clear for you the time advance, how it's used. And as I said, we cannot ask. So if we have let's say one frame, we cannot ask the mobile to send before the frame, so before the time of 5 millisecond. So that's why the maximum duration is 35 kilometer. Okay. So after presenting the timing advance, we will see together the different hierarchy of the frame. So we are already talking about the TDMA frame, which is consist of 8 time slot, and it consists of around 4.6. It's less than 5 millisecond, but it's 4.615 millisecond. And in GSM, we are able to have synchronization up to 3 hours. So we are able to have up to 3.5 hours because each frame here, it's a part of a big multi-frame. Okay? This multi-frame consists of 51 multi-frame, where each of them is 51 TDMA frame. So the period here is around 235 millisecond. This multi-frame, it's also a part of a big hyperframe, which consists of 2000 superframe, which is a period of 3.5 hours. So it's possible to allocate over this period of time in GSM because it's well defined in the standards. Okay, and why we are using this, remember that those are the physical channel. Each time slot here is a physical channel. So if I want to say that I want to use one logical channel every, let's say, 12 frame, okay, this means that I will use the first time slot here, and after 12 frame, I will use the same time slot. This means that I'm using one logical channel, okay, for this every 12 frame. Okay, I'm using this physical channel every 12 frame, which is one logical channel. Okay, and we are able to make this synchronization over a long period. So this is an important part of frame hierarchy. Okay, arriving at this level, let's see together the radio interface and the different channel. Here we are talking about the logical channel. Okay, so for the logical channel, we have, as we said, traffic channel, and we have the signaling channel, logical channel. And for traffic channel, we have the full rate and the half rate, and typically uplink and downlink. And for the signaling channel, we have two types, which are the broadcast channel, and we have the dedicated channel. The broadcast channel means that it's broadcast on the cell, and all user, all station, all mobile will take the information. Dedicated control channel means that it's dedicated to one mobile or to one user. Okay, and we have also the common channel. In the common channel, we have also downlink and uplink. So for the broadband, we have the frequency correction and we have the synchronization. For the common, we have the paging channel and the access granted channel. In downlink and in the uplink, we have the random access channel. And for the dedicated control channel, we have standalone dedicated channel, and we have the SACH and the FACCH. We will see them. So let's explain briefly what are the functionalities and how those channels are used. So for the traffic channel, it's a dedicated channel, okay, and it's used really to send the information of the user. So that's what we call user data channel, okay. And here, for because GSM was designed for voice, so over those channels we will send the voice data. It's also possible to use, as we used internet over GSM, we are using also uh, data over those traffic channels. So we have also the other dedicated channel. This is the traffic channel, and we have the here the control channel. Okay, we have the control channel. This was the traffic channel is dedicated, and we have the control channel. As a control channel, we have the slow associated control channel, the fast associated control channel, and the standalone dedicated control channel. The slow associated control channel is used to report signal quality management of the serving cell and neighboring cell to the network. Remember that, as I said before, and we will see this for the handover, in order to detect that now I have a bad channel and I have to trigger a handover for another, so we need to measure the signal quality. So that's why it's used to report the signal quality management of the serving cell. It's in uplink, and in downlink, it's used to send the power control command to the mobile device. So for example, the time advance I'm talking about is sent for the user or for the terminal or for the mobile in the downlink using the slow associated control channel. Okay, and as we said, it's not necessary to be sent every time slot. We will see that this is a logical channel that is mapped to a one-time slot every, for example, 20 or 24 physical or 24 frame. Okay. The fast associated control channel is used to send urgent signaling in case of handover. Okay, so that's why it's fast. Standalone dedicated control channel, it's really a pure signaling channel using during the establishment of the call. So when a user or a mobile want to establish a call, in this case, the first channel is the signaling is a standalone allocated channel. It's the channel used for signaling before doing the establishment and the assignment of the traffic channel. So this channel is used for signaling. It's not related to the call establishment, but sorry, it's used for signaling that's not related to the call establishment. So, for example, location update, it's used by another channel. We will see it is paging channel, and it's also possible sometimes to use this for. It's possible to use SMS message over the standalone dedicated control channel. Okay. Uh, we can use it also for location update procedure. Okay. For location update, and not for paging. Okay, paging are others, but for location update, it's also possible to use the standalone dedicated control channel. Okay. We have the synchronization channel. It's used to synchronize the mobile during the network to see, for example, in time, to synchronize with the good time slot with the clock. The frequency correction channel, in order to be able to know the exact frequency. So you have a broadcast channel that broadcast the frequencies, and the user will will use the correct frequency. In this case, it's used by the mobile device to calibrate their transceiver unit, and it's also used to detect the beginning of the multi-frame. And we have the broadcast command channel. In this channel, we have all broadcast information like system information that contain a variety of information like the code related to the operator and so on, the identification of the cell and the cell idea, all the information that are mandatory in order to be able to connect or to camp to the network. Okay, and typically this broadcast command control channel is monitored by all mobile device because it's a broadcast channel. The paging channel, it's used to inform idle subscriber for incoming call or SMS message. Okay, and the network is aware about the location area of the subscriber roaming in. The paging message is broadcast in all cell belonging to the location area. So that's it's related to the it's related to this one, but it's used really to broadcast the the information and to inform about the message, but the message itself is sent over the standalone dedicated control channel. Okay, and the location update procedure, some of them are done during using stand dedicated control channel. Okay. I will explain the paging. The paging is the procedure when the network has to search for a mobile device in all cells of allocation area for an incoming call or SMS. Remember that we said that the user will be in allocation area of a certain mobile switch center, we said, okay? And at certain time, if let's say we have a user here in this location area, and we have a message destinated to this user, in this case, we should look where the user is in order to forward the message to this user. That's why we should make a paging. Okay, so it's the procedure to search the mobile in all cells in order to forward the message to this user. And after that, the message is transmitted using the standalone SDTCH. Okay. And another channel, it's the random access channel. As I said, it's in uplink. And if the mobile device receives, for example, a message via a paging channel that the network is requesting a connection establishment, or if a user want to establish a call or send an SMS, in this case, we use the random access channel to initiate the communication. And this random access channel, in this case, will use the random, if you remember, the access grant burst. Okay. And here the access grant channel, where it's the confirmation is the subscriber send the channel request on the random access channel. The network will allocate an SDCCH, okay, in exceptional case the TCH, and it notifies the subscriber on the access grant via an immediate assignment message. Okay, it will contain. I mean, the network or the network will inform the mobile or the users about the SDCCH allocated and the TCCH allocated using the access grant channel. So contain the information about which SDCCH and TCCH the subscriber is allowed to use. Okay. So those are the main functionalities of the different channel, okay, control channel and also the data channel. Okay. So at this level, we are now aware about the different part of the radio interface and GSM and what are the different channels that are using. And now, after knowing the functionalities of each channel, let's see how we can do a radio network planning. Okay, so remember that the GSM concept was to create different cell in order to achieve the coverage of the users and to minimize the interference. So the objective is to be able to have minimum interference between them. And remember that we said in a cluster, that we should use a frequency once. So the frequency F will be used here, will not be used in the same cluster, it will be used in another cluster. And if you remember, we say that in case of interference between adjacent frequencies, so we try to use the adjacent frequency in separate cell. We are not using F1 and F2 that are adjacent in the same cell. We will use them in separate cell, for example, within the same cluster. So now let's see how we will do this radio network planning. So the radio network planning is the process to provide a cost-effective solution for the radio network in terms of coverage, capacity, and quality. So we should achieve the required coverage in order to in order to support the capacity, the required capacity with the quality. The objective is to offer this service with the quality. And remember that the quality, we will define it as the probability to make a call, okay, without being blocking. Okay. So the process of radio network planning starts with a collection of input parameters such as the network requirement, capacity, coverage, quality, and so on. And those input are then used to make the theoretical coverage and capacity plan. So we should have some information about the number of users that are available on this area, how much, what are the services used, how much data will be used by those users, those are the data. We need a specific tool to take into consideration the area, the environment we are working with, and we can use Erlang formula. We will see Erlang formula in order to make the radio site dimension. This means that we want to define the number of cells that we want to deploy in this area in order to be able to achieve the coverage and to support the capacity. So we will see this, what's a radio site dimension, how to do it. And after that, after having the number of cell in order to support the capacity we want, we need to see what are the best position of those cells. So we have what we call site survey. The engineer will go to the different area to see what's the right position to build or to put the cell. And after that, we should allocate the frequencies using a specific algorithm. We will see some example. And we should have the fixed network planning, and we should run the system to see if it's okay from coverage, capacity, and the quality. It will be okay in using specific tool like a simulator or a specific tool like TAMS or like NetAct Planner of Nokia or whatever. If it's okay, it's fine. If not, we will should try to update. Okay, this is a continuous process in a radio network planning. So I will start here by doing a kind of dimensioning. So how we can do dimensioning? In order to do dimensioning, the engineer will start the dimensioning from the cell site in order to define each cell site. Okay, what's the number of frequency to be used? What's the traffic to be covered by cell site? And after that, in order to do this dimensioning, we should know the geographical area to be covered, the estimated traffic in each area, in each region, the minimum requirement of power in each region, what's the blocking probability, which is the quality of service, what's the pass loss, what's the frequency use factor. Having all those parameters, we can define the cell. And after that, we should continue to see how to put the base station if you want to control one site or multiple site and so on. And after that, to dimension the interfaces that you want to connect. So how you want to connect the base station to the base station controller. Okay. And after that, the interface to connect to mobile switch center, and based on the expected number of users that you want to support in your system, what's the equipment that you want to use as home location register, as VLR. I mean the capacity of those equipment. Okay, so the first step is to start by the cells and the radio interface. Okay, and in order to do that, we should put the, let's say, the observation. So I'm planning this network over which period. Typically, if we start, we consider that we work, for example, around 6 months, for example. We consider that the evolution will the traffic will change every 6 months, for example, and you calculate the evolution of traffic between each two periods. And typically, if you want to consider your traffic at A, which is the time t0, okay, after one period, you should take A prime, which is A times 1 plus 20, which is considered as the increasing factor. It's due to the growth of the population of or the traffic, and it's also possible to add some security margin for your work, and you work in this A. So you work without working on A, you work on A, taking into account the growth of the traffic and a certain margin. Typically, it could be possible to be, for example, 10% or 20%, and the margin, for example, it's 5%. So in this case, it will be A times 1 plus 0.2 times 1 plus 0.07, and we work on this value. If we don't need to take into consideration this security margin, it's not necessary to multiply by this. We work on taking into account just the traffic increase. Okay. So how to do the dimensioning of the channel at the radio interface? This is a simple example. I know that you already did some dimensioning in telephony using Erlang formula. So it's similar to Erlang formula. So the idea here is to take the traffic per subscriber and to take the number of subscribers that should be supported in the area. And after that, you will calculate the all traffic, okay, that you want to support. And then based on the quality of service criteria, which is the blocking probability, you should use the Erlang formula in order to determine or to calculate the required number of channel in order to support this traffic. Okay. So I'm talking just here about the traffic channel. So let's give you a simple example. You have, for example, a traffic per subscriber, which is around 30 milli Erlang, okay, which is a busy hour. We are working always at busy hour. And we have a population is estimated at 500 subscriber. So what's the required number of channel in to support this traffic? If you have you need a quality of service with blocking probability of 1%, this means that it's 10 to power minus 2. So the probability that a client or a subscriber want to make a call and didn't find resource, didn't find channel, it's 10 to power minus 2. Okay, so we should find the number of channel that should support this traffic. So typically, if we have 500 users or subscriber, and each one will generate 30 milli Erlang. So this means that the total traffic A in this case is 500 times 30 milli Erlang, which is equal to 15 and 15,000 milli Erlang, which is 15 Erlang. Okay. So the question now is, if we want to support 15 Erlang, using the probability of 10 to power minus 2, how many channel are necessary in order to support this traffic. So this is will be determined using Erlang formula. Okay, so I will stop here. Okay, I have to check with you at which level you used uh, Erlang formula, and if you are aware about Erlang and the details about them. And I will continue to do some exercises in the next session. So I hope that you can review this chapter until this slide. Okay, and we will continue from this dimensioning exercise. Okay, thank you.